let's, why have I put a question mark over here? Any guesses? So what, I mean, the recipe of fixing alpha is equal to 1 is fine, there is no problem with it. In the 1D world, in the one dimensional world, I can fix, C delta t by delta x equal to 1, no problem. What happens when I go to higher dimensions? What was that relation between, I mean, if you remember, it was C delta t by delta s, delta x is equal to delta y. This was, in the case of 2D, what was it less than equal to? 1 by root 2 in 2D, and in 3D this was now I can't choose C delta t is equal to delta s because it has to be less than 1. So here can't set C delta t by delta s is equal to 1. Why? Because if I do it, what happens? I won't get a wave-like solution only, it's unstable, it's an unstable situation. So then what? Then you have to deal with it. The only fix to it is the second solution, right? And the second solution was by making your discretization finite, right? So let's, I mean, that's the same discrete version, right, which we had. So if you look at this equation over here, we started with this wave equation over here. In the case of 2D, what will happen? I will have a second derivative of y also, okay. So this dispersion relation, how do you think it will get modified? If I wanted to write this dispersion relation for, right, exactly. So this dispersion relation will become, using finite difference time domain, I am going to get, so I will write the time term first, sin omega delta t by 2, and I will get 2 terms, right, one from delta x and one from delta y. So now you would have to, I mean, the same analysis that we did in the previous slide, we would have to repeat it to generate the dispersion diagram over here. What is dispersion? Just the relation between omega and k. Wherever in optics or electromagnetics you hear the word dispersion, it means what is the relation between frequency and wave vector. That is what is meant by dispersion, okay. So this is a problem. So the only solution is small delta x, delta y, delta t. There is no fix to this thing. So what is a very, so now that we have to live with it, in 1D we can fix it, put alpha equal to 1, it is allowed, it gives me a stable solution. In 2D and 3D, I have no way around it. So what is sort of one very obvious consequence of this is, think of, let us say, a laser pulse. I want to simulate a laser pulse and it goes and hits some electromagnetic resonator or cavity or something, okay. As this laser pulse travels, let us say it is traveling in free space, right, it is going to numerically disperse because a pulse in time is made up of several different frequencies, but now each frequency has its own velocity, right. If you look at this curve over here, well, not in this curve, but for every different omega will have a different k. Yeah, once I fix the discretization, I will change the relation between omega and k at different omegas. So what happens is, supposing I set an input pulse like this, nice Gaussian pulse if you send like this, out what happens is it will get distorted, right. So you may, the output pulse, by output I mean the pulse seen after some space and time, right. So this may look something, why? Because the constituent frequencies that went up to make that pulse are traveling at different speeds now. If they all traveled at the same speeds, I would get the same pulse, right. So this is what is called pulse distortion. This pulse distortion, for example, will happen in an optical fiber because glass is a dispersive medium. Your optical fiber, glass, every frequency travels at a different speed. So, this anyway happens physically, but if I was simulating free space, this should not happen, but it will happen in FDTD. So, again the way to beat it is only one, small delta t delta x. Okay, so pulse distortion is what happens and it is a given in higher dimensions. There is another thing that you have to live with, and again the solution for that is making delta x delta t small, right. So, imagine a 2D grid like this. I send a wave, I send a pulse like this, it distorts. Now, I send a pulse like this, some other direction, what will happen? Because this discretization is finite, the approximations are now slightly different, right. So, now the wave travels at different speeds depending on which direction it is traveling in the grid. So, this wave and this wave, even if I choose a single frequency, okay, forget pulse, I send a single frequency tone as it is called, it will travel at different speeds here and at different speeds over here. There will be? Say, do not take this to be 45 degrees, take this to be any angle. So, the approximate, I mean because I am using finite differences to approximate the wave equation, it is more or less accurate depending on how well aligned you are with the grid, right. So, this is, so different directions, different speeds. Yes. The medium is isotropic is a statement of the physical properties of the medium. Air is isotropic medium, but by the virtue of me discretizing space and time, who is discretizing space and time? Not nature, we are doing it in our computer. The moment we do it, we have created an anisotropic material where none existed, right. So, different speeds and what, so yeah, I have already given the word away, this is called grid anisotropy. So, any real world simulation has all of these errors in it. There is no such thing as a perfect simulation. Perfect simulation happens when delta x, delta y, delta z, delta t is all so tiny, right. So, that is why, I mean one part of real world computational EM is writing your code, okay, very good, but after that you have to benchmark it with known solutions. You take simple thing like this, you write a 2D FDTD code and you think everything is great, then you run a pulse in different directions and you see, oh, it is behaving so differently. Then the next phase is in finding out what are the parameters delta x, delta t or Courant parameter such that the dispersion is acceptable. Let us say it is only 1%, you can live with that. If it is 20%, you can't live with that. So, you keep reducing your, making your discretization finer until you have reached some threshold. So, what can that threshold be? For example, my simulation domain is some fixed amount over here, and as the wave travels from the left to the right, the dispersion effects will grow more and more. As I reach the rightmost, like the two farthest points in the simulation domain, I can fix beforehand and say, okay, the dispersion from these 2 points should be no more than so much. I decide that beforehand. Then once I obtain that, then I do the rest of the simulations with those parameters. So, this actually takes almost as much time as code writing in the first place. Okay. Well, you could correct for dispersion effects if it were a very trivial simulation. Now, if they were only vacuum, sure, you can correct for it, but if it were only vacuum, what is the need to do FDTD? You know it is a plane wave everywhere. The more difficult things happen when there is some medium, some aircraft or whatever is there, right? There it is not possible to correct for these things. Because what is your bread and butter? Finite differences. How much more correction will you do in that? Again, those corrections will be direction dependent. So, you will introduce more problems by trying to correct it. So, you have to live with it. There is no other recourse. So, integral equations, so it's tempting to look at integral equations and say none of these problems were there, but integral equations we formulated at a single frequency. Yeah, at a single frequency, this problem, I mean, now, so in the integral equation, I'd have to do Fourier transform to look at pulse distortion. Yes, yeah. So that is, yeah, it's a good point. Integral equations are therefore the much more accurate ways of solving computational EM problems. FDTD is like your brute force guy. He gets you the answer after a lot of effort and is still not so good. Yeah. Yeah. So if you take a Gaussian pulse in time, it's Gaussian in frequency. Huh. Well, I don't have to worry about that. I've discretized delta x, delta t. Once I set my source, the wave travels. That the update equations take care of. For the integral equation, then I have to discretize in frequency, solve for each frequency, put it together. Yes, so discretizing frequency will bring its own errors, because depending on how fine you do it in frequency, that accurate is your solution in time, right? So then you have a trade-off, how much time do I want to devote to computation? So I mean, integral equations, at least in the optics community, are not very popular, right? People will do FDTD and pay the price in discretization. Okay, you want more accurate, just crank up delta x, delta t. Why? Yeah, I mean, numerically, once we have put it onto the computer, we are no longer going to see e to the jkx or e to the j omega t. We are going to see numbers, complex numbers. Then you can fit whatever thing you want to it, but you will find that even a 1D problem, if alpha is not equal to 1, right, it is not traveling at the speed of light. Even exactly, that's what we saw over here. Even when there is no medium, if you look at the dispersion relation, even when there is no medium, when delta x and delta t are finite, yes, you should not see any distortion in 1D if I set alpha equal to 1. But other places I have to live with it. Okay, so these are the sort of references for this. There's chapter 12 of Peterson's book, which is a very nice reference. There is the so-called Bible of FDTD. It's a book by Tafloff, which was one of the first few books written. And I found an interview given by Tafloff on Maxwell's equations and FDTD. So you can go and read this interview. He talks about, a little bit of history of Maxwell's equations and where he thinks it is going and so on. So do read this. All right.